Welcome to your lecture on thermochemistry. Today we are going to be looking at the Hess law and Hess law calculations. Now you are familiar, of course, with balancing a chemical equation. This is another way to see how chemical equations are balanced. What you've always balanced was the overall equation. Now we're going to take the overall equation and show you the minor or micro equations that lead to the overall equation, and we'll balance the equation in that way. So you do need a calculator because we are going to be talking about the delta H, which is heat, in kilojoules. So you are going to be adding, subtracting, multiplying, dividing as necessary. You also are going to need a pencil and paper or pen and paper so that you can write down notes, draw diagrams, write down critical information, any questions you have for clarity and understanding. Hopefully we will take care of those by the end of this lecture, but if not, please make sure that you get with your instructor so that you can get those questions answered before you take the assessment for this unit. So let's get ourselves started. In 1840, a German by the name of Hess, who was a Russian chemist, he came up with a law that said that the total enthalpy change during the complete course of a reaction is the same whether the reaction is made in one step or several steps. Now you should remember that enthalpy, which we're talking about, is actually the delta H, which is the amount of heat that goes into a reaction. He said that it can be used to determine the overall energy required for a chemical reaction. When it's divided into what he calls synthetic steps, these are the individual steps that occur before you get to the overall reaction. Now, a couple of things you do need to make sure that you understand is that we are talking about the law, that the total energy change or enthalpy change during the complete course reaction is the same whether the reaction is made in one step or several steps. What does that mean? Well, what we're saying is that enthalpy is what we call a state function. A state function is a function that it doesn't really matter how you get there. You just have a beginning and an end. The same as you get to, as long as you get to whatever that final state is, we call that particular pathway independent of each other. So a state function is an independent pathway. However you get there makes it a state function. So Hess law says then for the enthalpy or delta H, change in enthalpy for a process involving the transformation of reactants into products, it is not dependent on its pathway. Once again, it is not dependent on its pathway. So you can do it a single step, or you can do a bunch of mini steps in which to get that final reaction. Visually, that simply means that you all know that the shortest distance between 2 points is a straight line. Hess law says it doesn't matter if you go up, down, and around, or you take the longer route. As long as you make it to the final position, as long as you go from start and you get to finish, the reaction is still going to be the same. The amount of energy that goes into the reaction is the same. The amount of energy that comes out of the reaction is going to be the same. That's why it's a state function. It is path independent. Make sure you understand that term. It is a state function which is path independent. Okay. So let's look at some enthalpies. This is a little bit of review. We already know that exothermic reactions, of course you have the reactants and products, but if it's exothermic, we know that the delta H is less than 0. Therefore, the delta H's sign is a negative and energy is released. You should know this already, but just in case you've forgotten, make sure you write that down and make sure you remember that. When we're talking about an endothermic reaction where reactants are made into products, the delta H is higher than 0. Therefore, your delta H is going to be a positive, which tells us that energy is being absorbed. Once again, you should know that, but just in case you've forgotten, go ahead and write that down as a critical piece of information. So, go up here. For any chemical reaction, a change in enthalpy is going from reactants to products is constant. What does that mean? It means that for that chemical reaction, however you get from one place to another, however many micro, I call them micro, but little reactions take you to get to that final reaction, the delta H is going to be the same for that chemical reaction. However ways you break it up into smaller reactions, the delta H is going to be the same. So to calculate the overall delta H for a chemical reaction, the enthalpy changes for each individual reaction leading up to the overall reaction during the process get added together. And again, this is leading up to the overall reaction. And that Rx simply means reaction. Okay? So to calculate the delta H for a reaction, there are a couple of things you have to do. And yes, I know you probably thought it had gone away, but it's back. You have to balance each equation. That means the equations that lead up to the main equation, they each have to be balanced. Then the delta H for each one of those equations has to be assigned. And remember, whatever happens to the equation is what happens to the delta H. That is a big piece of information you definitely need to make sure you know within the information. Finally, we're going to add the equations together, and then we're going to add the delta H values. But you need to make sure you know that you have to balance each equation. That's a huge, huge thing. You cannot just go into there without balancing. Once you have the equations balanced, then keeping in mind that what happens to one equation happens to the delta H, then you can look at the rules. What do you mean by rules? Well, these are rules. I would strongly suggest that you take a picture of this slide, write it down, or some way keep it in your records. Okay? So let's look at what we're going to do. First of all, we're going to compare a substance in the available reactions to what it looks like in the overall reaction. That means we're going to look at the overall reactant, find the substances, or what we call the species, in the overall reactant, and then look for that species in the available equations that lead to the overall reaction. Once we've found it, we're going to ask two questions for each one that we find. One, is the correct substance on the correct side of the arrow? You know that there's an arrow between the reactants and the products, which is the yield sign. So is the correct substance on the correct side of that yield arrow? If the answer is yes, leave the equation the way it is. If it is no, you have to flip the equation, and more importantly, you have to change the sign of the delta H. So if your delta H is positive, when you flip the whole equation, then you have to change the delta H to negative, and vice versa. Your second question on that species, is the coefficient for that species correct? If it's yes, then you leave it alone. Still leave it alone. And if no, then you're going to have to either multiply or divide distributively, that means throughout the entire equation, to get the correct coefficient for that substance or species. And again, you have to do the same for the delta H. These are the two rules that you're looking at, okay? Those are the two rules you're looking at. Now, once the decisions, number 1 and 2, are made, whether you're flipping it or leaving it the same, you're going to lock the equation or the reaction in place. That means you do not go back to it to rework it. It's set. You can work on any other equation but that one. If the substance or species occurs more than once in the reactants that are available when you go to do the comparison, then look at it last. And then once all the reactions have been determined, then you eliminate what remains using the same method. So once you determine all your reactions, then you go back and you say, okay, I can't use the ones that I've locked, but if I got extra reactions left over then I use those to do the elimination of what I don't want. And when we do the elimination, remember, we want to make sure that whatever's on one side is on the other side, so it can be eliminated from the overall reaction because it doesn't belong in the overall reaction. Now, I know that sounds kind of wonky, but like I said, we're going to go through these so that you can see what I'm talking about. So, FYI, make sure that you know this information on how to work that equation. And then all we're going to do, only thing you do from that is to just do them. So, I hope you got your pencil, paper, hope you got your calculator. Let's get started. Look at the first one. I'm going to walk you through so you can see what we're talking about. This is lead 2 chloride solid plus chlorine, gas leads to lead 4 chloride, and for some reason it's a liquid. A couple of things. You have to make sure you look at the correct equation and always make sure you have the correct state. You'll find that some of these equations you may have the same formula, but it may be a different state. So those are the two things that we have to match up. The equation and the state. I'm going to write that down, or the formula and the state. Make sure your formula and state are the same to compare. That means that if I'm looking at PbCl2S in my final equation, then I'm going to be looking for the PbCl2S in the available equations. So, here are your two equations or reactants. As you can see, you have Pb and Cl2 and PbCl4 liquid and Pbs and Cl2 gas and PbCl2S. But please note that the only things that are in the final equation is PbCl2 solid, which is here, Cl2 gas, which is here, and PbCl4 liquid, which is here. Well, we've got all the things we talked about. We've got the species that match, and we've even got a species that's occurring multiple. Remember what you're supposed to do with the ones that occur multiple. We're not even going to try to address those. We leave those till last until we get everything else locked that we want, and then we'll go back and deal with it if we find it necessary. So, what are we going to do? We're going to compare each reactant and product to those in the given equations, and then we're going to multiply or divide and or flip the given equation to match what we're trying to find in our overall equation. And if a substance appears in more than one given equation, then we're going to skip it. So let's see what we got here. If we look, we find that if we check out the PbCl2 solid, we find it only once in the available equations, PbCl2 and solid. But notice where it's located. There are two questions. Remember, we asked, is it on the correct side? And we asked, does it have the correct coefficient? Okay, so looking at this, we find that the PbCl2 solid is not on the correct side. So if it's not on the correct side, remember we said we were going to flip it. Next question, does it have the correct coefficient? Well, this has a coefficient of 1 in the equation, or the final overall equation rather. It has a coefficient of 1. And in the available equation, it has a coefficient of 1. So, yes, it has the correct coefficient. So, all we had to do with this was to flip it. Next thing we're going to look at, and again, we see that the Cl2 gas is multiple. So, we're going to leave this for last. We're not even going to try and address that. That's just too much to look at. Let's look at something else and see if we can get the other equation set up. Let's look at the PbCl4 liquid. Here's PbCl4. Again, question number 1, is it on the correct side? When we look at this, we see that this is on the reactant side and this one is on the reactant side. So yes, it's on the correct side. Second question, does it have the correct coefficient? Well, the coefficient for PbCl is 1 here, and the coefficient for PbCl is 1 here. So yes, it has the correct coefficient, and yes, it's on the correct side. So we're going to leave this as the same. Okay, now this is what we've done. Now let's confirm ourselves by going through the PowerPoint. When it's rewritten, we find that 1 stays the same, but the second one, see right here, even they agree with us, it has to be flipped. So the second one gets flipped entirely. That means that what was the products now become the reactants. What were the reactants now become the products. And look what we've had to do to the delta H. Because we flipped this, the sign of our delta H has gone from a negative to a positive. Take a moment and look at that. Look what we did. We flipped the equation. We made the product the reactant the products. And because we flipped the equation, we had to change the sign of our delta H. So here's your equation. And then we add up all the products and reactants on one side. Now there are 2 ways you can do this. You can eliminate what needs to be eliminated, or you can write them all down and eliminate them that way. But once you have these locked, if we write them all down, that means that we take everything on this side and bring it down. And we take everything on this side and bring it down. We get our reactants from here. And we get our products over here. And then once we look at that, we decide, okay, so what can I possibly cancel out? We add our delta H's together, which is going to give us 30.2 positive kilojoules. And this is how we check. Once we've canceled everything out, if it matches the top or final reaction, we know that we've done it correctly. So let's see what can cancel. Okay, let's see. I'll do it myself so you can see it. So we can get rid of this PBS solid because it's on both sides. Look at here, we have a chlorine 2 gas on this side, 2 chlorine 2 gases on this side. Well, just like you did balance equation, if I can get rid of 1 chlorine from both sides. And then when I bring everything down, look at what we got. I'm going to have the PbCl2 solid, which we have here, the Cl2 gas, but only one of them, which works. Those are all on my reactant side. And then the PbCl4 liquid, which we have here. Okay, so when we bring it down, we have exactly what it looks like at the top. So this reaction is the same as this reaction. It doesn't matter whether or not your reactants are in the same order. Just make sure you have all your reactants on one side and all your products on the other side. And of course, the positive 30.2 kilojoules is correct. So easy, right? Because they all match. We know we got it right, right? Easy, right? Okay, let's do another one. Pause this if you need to. Write down whatever questions you have, and then just press play and continue. Okay, this one. we have 2p solid, phosphorus solid, plus 5 chlorine gases produces 2 phosphorus pentachloride solid. Okay, the reactants available are here. So again, we're going to do the same thing. We're going to work it, and then we're going to check ourselves to see if we got it right. All right, so first thing we're going to do is we're going to look for 2p solid and make sure it only occurs once. It does. It occurs right here. So we're going to ask ourselves that same little question. Is it on the correct side? When we look at this, we say yes, it is. It's on the correct side. Our next question is, does it have the correct coefficient? And when we look, this has 2p, this is 2p, so yes, it has a coefficient. So then we're going to leave this one the same, and we're going to hope that theirs matches up to ours, right? Okay. All right, so then let's look at the next species. This is chlorine 2, Cl2 gas, but we find we have one here and we have one here. So what are we going to do? Same thing we did before. We're just going to ignore this right now. We're just going to skip it. And unless we have an available reaction that doesn't get locked in, it should work itself out. Okay? Now let's look at the 2PCl5 solid. Here's PCl5 solid. Actually, you know what? I'm going to change the color. So it probably make it a little bit easier for you to follow with me. There we go. Here we go. All right. Same thing. Question number 1. Is it on the correct side? Probably wasn't the best color to choose. Okay. No, it's not. So what do we have to do? We have to flip it. Next question is, does it have the correct coefficient? Well, this has a coefficient of 2. This has a coefficient of 1. So no. So what am I going to have to do? This green is killing me, guys. I'm sorry. I need a little bit darker. I'm going to have to multiply that by 2, because 1 times 2 is going to give me the 2 that I'm looking for. Okay, and if I multiply this by 2 and I flip it, what am I going to do to my delta H here? Well, since I flipped it, my delta H is going to go from a positive to a negative. And since I've multiplied by 2, I have to multiply my delta H by 2. I have to multiply my PCl3 by 2. I have to multiply my Cl2 gas by 2. Remember, it's distributive. Distributive. So it has to be distributive. If I have to multiply the PCl5 by 2, that means I've got to multiply everything in that equation by 2. So it's going to be flipped and multiplied by 2. Okay, so let's see how well we came out of that. Do we have to flip it? We do have to multiply the first one by 2. And the second one we leave the same. Okay, so when we rewrite it, we have this equation flipped. And we've multiplied all of our species by 2. Notice that the reactants are now over here, as the products are as reactants, and the reactant is our product. So we flipped it and we multiplied that by 2. Also notice that we've taken our delta H here, we flipped the sign, so it's now negative, and we multiply it by 2. Okay, so what we did to one side, we definitely have done to the other side. The second equation, of course, stays the same because everything was perfect. So then what we're going to do, same thing before, we're going to add up our reactants and products, and we're going to add our delta H. So we're going to take all, make this red, we're going to take all of our reactants and bring them down on one side, and we're going to take all of our products and bring them down on one side, and then we're going to take our delta H, another color for that, and we are going to add negative 175.8 to negative 574 and add those all together. And when we finish, we should wind up with this equation. So here we have added up our delta H to get a negative 749.8 kilojoules. And we have all of our products on one side, all of the reactants on the other side. So now we can eliminate if we see the need to do so. So let's see what can be canceled out. On the reactant side, we have 2PCl3, which is not in our overall equation. So we can cancel it here as well as here because it occurs on both sides. We have 2Cl here, and we have 3Cl2 here. So these two are going to come together to make 5Cl2, the gas, which is what we want because it's up here. And then we have 2P, which is what we want because it's right here. And we have 2PCl5 solid, which is on the other side of the products, which we have here. So it looks like we put them together the way they should. And here's our answer. Quick reference. This final equation looks like this derived equation. And so this is our delta H, which tells us that this is exothermic. Okay. All right, pause, make sure that you understand what we did. And then we'll move on when you're ready. Okay, this time we have phosphorus for solid. We have 10 chlorine gases. We have 4 phosphorus tetrachloride gases. Okay. And our equations are here. All right. So let's see what we got to do with it. We're looking for P4 only once, and it does. It occurs right here. The question, is it on the correct side? We notice that it's a product. It should be a reactant, so no. We have to flip it. Second question, does it have the correct coefficient? We find that this has a coefficient of 1. This has a coefficient of 1, so that is correct. So we can leave that one as just a flipped equation. Now remember, when I write flipped, I've now locked it in. I can't go back and work on it. All right. Then we're going to look at, I'm going to get another color, chlorine. Well, once again, chlorine occurs here and here. So once again, we're going to act like we don't even see it. We're going to totally skip over it. And we're going to look at PCl5. Okay, and where is PCl5? Oh, here's PCl5. Okay. Question, is it on the correct side? And we see that it is a product in the final reaction, is a product in the available reaction. So yes, it's on the correct side. Second question is, does it have the correct coefficient? In this case, there's 4 here and there's only 1 here. So no, I'm going to have to multiply it by 4. And remember, if I multiply it by 4, it's distributive. So I have to multiply everything by 4. I have to multiply all of the species of the equation by 4. And I have to multiply my delta H by 4. I don't have to change the sign because I'm not flipping it. But I do have to multiply my delta H by 4. So look at it carefully. And then we're going to check ourselves. Okay. So, according to this, the first one is flipped. Again, we see that our reactants are our products. Our products are our reactants. So we did flip it. Our sign, delta H, went from a positive to a negative sign. For the second equation, we said you had to multiply it by 4, which they did. And remember, we said it had to be distributive. So here we multiply all of this by 4. We multiply this by 4. This is going to give us 4 PCl3. This is going to give us 4 chlorine gases. This is going to give us 4 PCl5. And if I multiply negative 67 times 4, I get a negative 268. So that's exactly what's happened. Then we're going to rewrite them all together. When we add our delta H's up, we get negative 918 kilojoules. And when we put all of our, change my colors a little bit, we take all of our reactants and put them together. And then we take all of our products and put them together. And then we can play the elimination game. So let's see what our elimination is going to be. I need the P for, because I got it up here. I've got 6 chlorines here and 4 chlorines here. Together they're going to make 10 Cl2 gases, which is fine because I got that up here. I've got 4 PCl5 gases on the product side, and I got them up here. That leaves me with 4 PCl3. I've got a 4 PCl3 on the reactant side, 4 PCl3 on the product side. I can cancel those out. And my final equation looks just like my overall equation. And my delta H is a negative 918. So this is exothermic. Okay. All right. Now this time, we're going to do this together, I believe. Let's see what we have. This is 3. A little bit different, a little stretch, but we can get this done. Okay, so with this one, we need to find sulfur, and we find, this is our sulfur solid. We find sulfur solid here. Is it on the correct side? No, so we're going to need to flip it. Does it have the correct coefficient? No, because there's a 2 in front of it. It's not a 2 there. So we're going to multiply that by 2. Let me see. Next we're going to find water. How many times does it occur? I only see it one place, right here. Question, does it have the correct coefficient? Is it on the correct side? Yes. Both of them are reactants. Does it have the correct coefficient? No, because this water has a 2 and this one does not. So we're going to multiply this by 2. Okay. And then we're going to look at 2H2S, the gas, which only occurs once, right here. Is it on the correct side? Yes. Does it have the correct coefficient? Yes. So I'm going to leave this as the same. And of course we have oxygen, but look where oxygen occurs. Here and here. So we're going to do what we always do. We're going to leave that alone and leave it all by itself. So let's look at this one. This has not 1, not 2, but 3 equations. So we're going to do the same thing we did before. We're going to figure out what goes where. So let's see. We have S solid, and there's only one S solid right here. First question, is it on the correct side? No, it is not, so we're going to have to flip it. Second question, does it have the correct coefficient? No, it does not, because there's a 2 in the final equation and there's only a 1, this one, in that equation. available, so we're going to have to multiply this by 2. And if we do that, that means we've got to flip the sign of our delta H from positive to negative because we're flipping it, and we've got to multiply our delta H by 2. All right, now let's look at water. There's H2O liquid, and I only see one H2O liquid here. Question is it on the correct side? Yes, it is, because they're both reactants. Does it have the correct coefficient? No, it doesn't, because there is a 2 here, and there's only a 1 here, so we are going to have to multiply this by 2 distributively, which means our delta H is also going to be multiplied by 2, but we're not going to change the sign. And then we have H2S gas. Let me give this another color. And I only find it once here. Is it on the correct side? They are both product sides. Yes. Does it have the correct coefficient? Yes, because there is a 2 in the final and there's a 2 in that available. So this one I'm going to leave the same. And of course we have oxygen. But the problem with oxygen is there's an oxygen here and there's an oxygen there. So what we're going to do, we're going to act like we skip right over there like we never saw it. And since all 3 equations are already locked in place, we're just going to hope that it works itself out. Okay, so let's check and see if we got it right. Remember, we had same times 2 flipped in times 2. So equation number 1 stays the same. Equation number 2 is multiplied distributively. So we've got 2 H2Os, 2 SO2 gases, and 2 H2SO3 liquids. So we know that worked. And our third, we had to flip and multiply by 2, and that's what they did. They flipped it and multiplied it by 2. Our reactants became the products. Our products became the reactants, and we had to multiply it by 2 distributively. So we have 2 S solid, 2 O2 gas, 2 S2O2. Okay? When we look at our delta H's for the second equation, remember we had to multiply this by 2. That gave us negative 93 kilojoules. And for the third, we had to not only multiply it by 2, but we also have to flip the sign so it becomes a negative 445.6. Okay? We're on a great track here. When we write them all down together, woo, there's a lot. We add all of our delta H's together, and that gives us negative 232.6 kilojoules. And when we look at all our reactants on one side, our products on one side, now look at the way they've got it. Our arrow is right here. So that means these are all products, okay? So let's do the process of elimination. Let's look at what is ours and look at what's left. We have 2S2 solid, and there's a 2S2 solid. We have 2 H2O liquid, and here's your 2 H2O liquid. That's everything we have on the reactant side. On the product side, we're looking for 2 H2S gas, and here is 2 H2S gas. And then we have 1 oxygen. Well, we're hoping this worked itself out, so let's see. On the reactant side, we have 2 oxygens. On the product side, we have 3. So both can lose 2 oxygens, making that into 1 oxygen, which is what we need right here. So we have what we need right here. Everything else should be able to cancel. Well, let's look. We have 2 H2SO3 on the reactant side and 2 H2SO3 on the product side, so we can cancel those. We have 2 SO2 gas on the reactant side and 2 SO2 gas on the product side, so we can cancel those. Okay? And so, when we bring them all down, They should exactly match our final equation. And here you go. This is our final equation, and it's the same as this. And our delta H is a negative 232.6, so this is exothermic. Okay? Okay, so you've seen how it's done. Excellent. Let's try this. This time we have not one, not two, but three equations. Okay? And so we are going to do the same thing. We're going to look for C, carbon solid. And there's only one in here. Is it on the correct side? No. So you're going to need to flip. That means I'm going to need to change my sign to a negative right here. And does it have the correct coefficient? There's a 1 in front of the carbon in the original. There's 1 in front of the carbon on the available. So yeah, that's good. We're going to look at oxygen. Let me give it another color for that. O2. And I find I have an O2 here, and I have an O2 here. So I'm going to go coward, and I'm going to erase this. I didn't even see this because that is going to be way too hard to do. And we can hope for the best, hopefully, but we'll see. We may have to address it again. I don't know. It looks like we're going to have to, but for right now, we're just not going to address it right now, okay? All right, so let's look at CO2, the gas. And I find CO2, the gas, here in this equation once. Is it on the correct side? No, so I am going to have to flip it. Does it have the correct coefficient? Yes. All right, so everything's been locked except for the O2, and we know that O2 occurs twice. All right, so if you have a free available equation after you've locked all the ones that you can, then we deal with elimination. I am still not trying to approach that oxygen. Notice that. I try to deal with elimination. So what do I mean by elimination? Well, I know that I do not want an H2 in my final equation. So I have to eliminate it, right? Okay. So I need to find the H2 in my locked equation that's going to be eliminated. See if that works. Well, if I look, I see that this equation, which is going to be flipped, is going to be putting H2 on this side. And if it does that, then this first equation, which doesn't have any designation on it, if I flip that first equation, I'm going to wind up with 4 H2s on the reactant side. But if I leave it the way it is, I'll be able to eliminate this H2 because it will be on the reactant side, and I can eliminate this H2 because it'll be on the product side. So I'm going to leave that as the same. Okay, so this is what we're going to do. Now let's see how well it works. Again, I'm not trying to look at oxygen. I'm just trying to do elimination. So let's see how well this works. So our first equation, we're going to have 2 H2O liquid produces 2 H2, the gas, plus O2, the gas. And our delta H is going to stay at positive 342 kilojoules because we left it the same. Our second, we have to flip. We're not doing anything to it. We're just flipping it. So our products become our reactants become our products, and of course, because we're flipping, our delta H sign is going to change to negative, right? Okay. So this becomes 2 CO2, the gas, plus CH4, the gas, produces CO2, the gas, plus 2H2O, the liquid, and our delta H is a negative 534 kilojoules. Okay? And our third one, we're just going to flip. So our products become our reactants, reactants become our products. This is going to become 2H2, the gas, plus C, carbon solid, produces CH4, the gas, and our delta H is going to change to a negative 45 kilojoules. All right, let's look at what I want and see if I get everything I want. And hopefully that oxygen is going to work itself out. Hopefully. All right, I need CS, carbon solid, and I do have carbon solid on the reactant side. I also need oxygen on the reactant side. Well, I've got an oxygen here, two oxygens. I got one oxygen, so they can both lose an oxygen, making that a 1. Okay, that gives me my one oxygen on this side. Yay, oxygen's taken care of. And I have CO2, the gas, and on the product side, and I have my CO2, the gas, on the product side. It means everybody else should be able to eliminate from each other. So let's see if they eliminate. This is CH4 gas. I can eliminate that because I have CH4 gas as a reactant also. This is H2O, the liquid, on the reactant side. I can eliminate that from H2O, liquid, on the product side. And this is 2H2 gas on the product side. I can eliminate it from 2H2 gas on the reactant side. Okay, so if I rewrite everything, I wind up with O2, the gas, plus carbon solid, produces CO2, the gas. And if I add up my delta H's, ready? You want a positive 342 plus negative 534 plus negative 45. You should wind up with a negative 237 kilojoules. Okay, and when I compare my reaction, the one I derived and the one that is original, I find that my derived and my original is the same. Once again, doesn't matter that I have O2 before carbon, as long as I have my correct coefficients on the side they're supposed to be on, and I have my correct products on the side they're supposed to be on. Okay? All right. Good job. Now, I would recommend that you go back and do those problems that we just went over so you can get comfortable with those. And then, of course, do all the examples and the worksheets that you're given by your instructor. If you had any questions that were not answered by this lecture, I strongly recommend that you get with your instructor and make sure that you get those questions answered before the assessment for this unit.